Now that we have all the tools required to derive the capacity of additive Gaussian noise channel, we will establish this formula saying that the capacity of a additive Gaussian noise channel is half log 1 plus SNR, the signal power by noise power. So we will start with the lower bound first, the so-called converse bound, converse part. In the converse part, we will show that this capacity cannot exceed half log 1 plus SNR. And in this part of the proof, we will use the ideas of differential entropy that we established earlier. So suppose we have a code of size m, length n, satisfying power constraint, satisfying the average power constraint. So what does that mean? It means satisfying the average power constraints, that is, each code word x has 1 by n summation I equal to 1 to n x I square less than equal to p. Yeah, so various conditions: size m, length n, satisfying average power constraint, and finally, and with average probability of error less than equal to epsilon. This is the fourth condition. Suppose all these holds. So let's say let xn be the input of the channel when a message u distributed uniformly over 1 to m is sent. Okay, so that is, again, this xn equals to is equal to e of u. So you have this message u which is distributed uniformly over 1 to m, and then you use your favorite codes encoder and send xn, and then this xn is sent over the channel, additive Gaussian noise channel, and you receive yn, and then you apply your decoder to this yn and you get this u hat. U hat is the decoded value. Okay, these are our notations. The codes are xn and then u hat is the decoded message. Suppose you then, by Fano's inequality, this is the same step as before. Log m which is the entropy of, which is the same as the entropy of this random message, uniform message u, which is also equal to the mutual information between u and u hat plus the conditional entropy. And now this conditional entropy can be bounded by Fano's inequality. This guy is less than epsilon log m. This second term is less than epsilon log m plus 1. So that is 1 minus epsilon times log m is less than the mutual information between u and u hat plus 1. Okay, so this is the same step as before by Fano's inequality. But this is all in discrete world because both u and u hat are discrete. And now, by data processing inequality, we can switch to the continuous world. So this mutual information between u and u hat, it's less than equal to the mutual information between xn and yn. This is the data processing inequality that we stated earlier, but we never proved it. It is it follows from the fact it follows from the data processing inequality for Kullback-Leibler divergence, but it's slightly technical because we've switched from discrete distributions to continuous distributions. Okay, so but it's quite believable. So this one holds, and now note that since yn has a density given xn, yn has a density, and therefore we can talk about its differential entropy. So we can write it as h of yn minus h of yn given xn, and we can do this since yn given xn is Gaussian, yn has a density. So we can talk about differential entropy. Okay, and therefore this second term here, h of yn given xn, this guy here, given xn, this yn is just a Gaussian with mean xn and variance sigma square I. Therefore, its differential entropy can be evaluated as before to log 2 pi n by 2 log 2 pi e times the variance. Okay, so this is the first step. This is more or less equality. Now what do we do with this remaining h of yn? We note that the variance of each yn, so let's look at the summation I equal to 1 to n, expected value of yi square. What is this variance? This is equal to summation I equal to 1 to n, expected value of yi square given xi. Okay. Now given xi, this yi is just a Gaussian with mean xi and variance xi and variance sigma square. So this is equal to summation I equal to 1 to n, expected value of mean square, which is xi square, plus the variance, so that's sigma square. Okay, but then we already know that, so we can just take this summation inside, so it becomes summation I equal to 1 to n xi square plus n sigma square. And now this is where we bring in the power constraint. Since summation I equal to 1 to n xi square is less than equal to np with probability 1, because that's the power constraint, we get, in fact this bound will hold even when this holds only in expectation, but this is what we required. So even if you had this power constraint satisfied in expectation, even then this bound will hold. Okay, so now we have expected value of yi square is less than equal to n into p plus sigma square. Okay, we get this bound. So very nice. So now this vector y1 to yn satisfies this power constraint, and earlier we saw that Gaussian maximizes, recalling that the Gaussian distribution maximizes entropy among all random variables with bounded second moments, or with second moments bounded by, with second moment, actually among all random vectors with second moment bounded by a constant. In this case that constant is np plus sigma square here. So we recall that and from that we get this, that this differential entropy of yn must be less than differential entropy of a corresponding Gaussian with zero mean and and this variance, this times I, okay, this pi n times I, p sigma square times I, and therefore this we already evaluated. This is just n by 2 log 2 pi e. This is the third property among all the properties we saw earlier. Okay, so these are the different inequalities that we get. Let's collect everything. This is the first one that we saw. Log 1 minus epsilon log m is less than equal to mutual information between u and u hat plus 1. And then the mutual information itself here, this mutual information equals the differential entropy of this minus this. And then at the end we saw that this is, so if you see everything together, let me zoom out to see everything together here. Hopefully I can see everything together. Yeah, still not. Okay, so yeah, barely you can see everything together. Let's see everything together. Right, so these are the three inequalities we have. So let me do it here. Oh, sorry, let me just bring it down. That's all right. So by 1, 2, 3, 1 minus epsilon log m is less than equal to this mutual information plus 1, but mutual information is this, and that's less than this. So you get n by 2, this is the upper bound on binary entropy of y, 2 pi e p plus sigma square minus n by 2 log 2 pi e sigma square plus 1. So this is simply n by 2 log 2 pi, so 2 pi e cancels and you get p plus sigma square by sigma square. That's 1 plus SNR and then plus 1. And therefore any epsilon achievable rate must be less than half. So we divide by n and take limit n going to infinity, half log 1 plus p sigma square. Okay, and this is, oh sorry, a factor of 1 by 1 minus epsilon. And therefore if a rate is epsilon achievable for all epsilon, so we can take limit epsilon going to 0, and that implies Cp sigma square less than half log 1 plus p by sigma square. Okay, that's the proof of the converse. Note that this is a weak converse because we don't have the same bound for every epsilon. In fact, a strong converse can be established using what we saw earlier for the binary symmetric channel, namely the sphere packing bound, except that the spheres now will now not be for the Hamming space but for the Euclidean space. Okay, so this is the proof of converse. This must be less than equal to this. Okay, so now moving to the second part of the proof, we will now prove the achievability of the result. Yeah. Okay, so now the first part is done. Second, we prove the so-called achievability part. Okay, so this will just say that we can find a code, we can find a sequence of code whose rate exceeds half log 1 plus SNR. Okay, so to show this part, we recall our single shot achievability lemma. So recall, this was done in unit 13. Suppose for lambda greater than equal to 0, we have probability under xy of a set of all xy, such that earlier we had log likelihood ratio, but now we are talking about the more general version. So we'll have the Radon-Nikodym derivative. This is the replacement of log likelihood ratio. This guy greater than lambda. This is the acceptance region of a hypothesis test of pxy versus pxpy. Suppose this is greater than 1 minus epsilon, and under this condition we saw we saw earlier that under this condition then we can there exists a code. This is a single shot result of size this with average probability of error less than equal to epsilon. So this result we showed earlier for the discrete case, and now in the general case, the claim is that the result goes through for general case. Remember what that, I think the probability of error was less than 2 epsilon. Remember what that code was? The code was that for each xm, so we think of this as the acceptance region, the region where we'll accept pxy over pxpy. And for each xm, if you see a y, you accept that xm if xm comma y belongs to this acceptance region. Okay, and in fact you accept m as the message if m is the unique message for which xm comma y lies in the acceptance region. Otherwise you reject m, and you generate a random codebook to xm, and you show that the random codebook satisfies this. Okay, that was the proof. The claim is the same proof goes through now, even in this case. Okay, that proof didn't require anything. It just requires you to change measure from one to the other, and now we have a nice bound for those measure change log likelihood ratios, and so the same proof will go through. I will not repeat that proof. So what can we do with this proof? Are we done? Well, it doesn't quite solve all our problems. First, we note that for the Gaussian case, these things are just this can be computed. For Gaussian channel, this guy here is simply the density of x. Let's denote by density of y given x, which is just the Gaussian density. Okay, divided by density of y, which is the mixture of these Gaussians. So fine, so this thing can be computed, that's not a difficulty. But the difficulty is that we want the code words to satisfy power constraints. So we want the code words to, we want the code words to come from a set E. Okay, that's what we want. Corresponding, this E is for an event, corresponding, not corresponding, set E. So what is the set E that we'll choose? Firstly, we will apply the single shot result to n IID repetition, and we will choose E to be those x for which 1 by n summation I equal to 1 to n xi is less than equal, xi square is less than equal to np. That's the E we would like to choose at the end. Okay, so how do we modify this proof so that this condition holds? Well, let's do the following. So this is again, we only need to verify this condition, and the way we do this is we will restrict our code to this set of code words which to a distribution which is supported on this set E. Okay, that's what we will do. So how do we do that? So let's directly do this thing for the n-fold case. Let x tilde 1, x tilde 2, x tilde n be IID Gaussian with mean 0. This is the distribution that we are choosing. The single shot result holds for any distribution. And variance p minus eta. We are backing off a little bit from p. And let the actual distribution that we used in the discrete case was an IID distribution. But now we will use the full power of a single shot achievability and apply it to a non-IID distribution. Okay, which is not so far from the IID distribution. This is the distribution obtained with the distribution Pxn defined as the conditional distribution of these random variables, the Gaussian random variables, given that the vector xn, x tilde n belongs to this set E. Okay, I'll define this later. So I'll say given E, any set E, it's the conditional distribution. Conditional distribution of x tilde n given E. Okay, the event E. And now we make an interesting but simple but interesting observation that if we look at the density of y tilde n, this is the vector that you see under this, the output of this distribution when these are passed through some channel. And if you look at yn for the same point, so let's just look at this ratio of densities. So this is the ratio function evaluated at yn, which is the ratio of these two functions. Maybe it's better to write it that way. Yn. This guy here is equal to, what is the numerator? Numerator is, you will take the integral of this guy. So y tilde n given x tilde n, yn given xn, f x tilde n xn dxn, and integrate it over everything. And in the denominator you have condition on E, so you will integrate only over E, the same thing. So the channel output when the input is xn. Okay, and this of course can be bounded below by, because everything is non-negative, by just integrating over this is the channel output when yn given xn, and this is f of xn xn. So we can even restrict the numerator to that set E. Problem, it's only reducing things. And now, since the channel is the same, so f of yn xn is equal to, that's how we are setting this, is equal to this thing. Only the input distribution has changed. In tilde we didn't have the conditioning on E, but we use the conditional distribution here. So that's the only difference. So what is this thing? This is exactly equal to, so these two are same here. F of xn is f of x tilde n xn given probability that x tilde n belongs to E. That's exactly what it is. Therefore, this distribution is exactly equal to probability that x tilde n belongs to E. Okay, that's what this ratio. This ratio must exceed this one. This is an observation. Therefore, the log likelihood ratio of the actual distribution that you're using, so log likelihood ratio f of yn given xn by f of yn exceeds the log likelihood ratio of, so we can we can replace this by f of y tilde n given x tilde n. That's equal. These two quantities are equal, and this we have multiplied it and multiplied and divided by this y tilde n yn. And the maximum change you will make when you multiply and divide by this is plus log probability x tilde n belongs to E. Note that this is less than 1, so this is, you're just reducing it by some amount. Okay, so this bound holds. Thus, if you look at the probability under the actual measure that you use, this is your conditional. So once again, I've never elaborated this. What is this xn yn? You use the conditional distribution for xn, and yn is the output of the channel when xn is the input. So if you look at these guys, what is the bound that we have for log likelihood ratio? So that's log of, so the probability that this x and yn satisfy, let's say xn yn by f of xn yn exceeds lambda. This probability, because of this calculation here, exceeds the probability that under xn yn we find some xn and yn such that, we'll switch to this one now, log of f of x tilde n y tilde n xn yn by f of x tilde n xn of y tilde n yn plus, so I'm just using this. So if this is greater than this, the right way to say it is, just 1 second. Yeah, so if this guy is greater than lambda, but because this guy exceeds this guy, therefore this guy must be greater than lambda. Therefore this is a lower bound on this. Okay, but note that we would like to move the entire calculation to x tilde y tilde because that's our original IID distribution, and then we can use law of large number to set this parameter lambda modulo this part which we have to handle, but this is under x and y. Okay, well, so how do we bring in x tilde y tilde? So we will first write it as 1 minus e x and yn, the same set such that this is less than whatever it is, this is less than lambda, this is less than lambda. And now we note that if we restrict to xn in E, so this is only xn in E because we are computing probability under x and y. Now when you convert this guy to probability x tilde n, you will have conditioning. All the xn probability will have a conditioning over that xn belongs to E, so that's a division, no problem. Further, this thing will only be restricted to xn in E, but you can allow any xn, but that will only increase the thing. Therefore, went to this reasoning fast, you can think about it again. This is like greater than x tilde n y tilde n of x n y n log same expression here. Is less than lambda minus log. Okay, this is fine, except that you divide by this probability that x tilde n belongs to E. Okay, so that this bound holds. So this is very nice now. So all this calculation is for the IID case. So we just have to verify a bound for the IID case. If we have a lower bound on this for the IID case, we'll get a lower bound for this distribution as well. So note that by our choice of E is this set here, okay, and we're choosing this. E is the set of those x for which this guy is less than or equal to NP, but these are IID with with variance p minus 1 eta. So therefore, they're by law of large number for sufficiently large n, this must hold. That everything must belong to E. So for by the law of large numbers, the weak law of large numbers to be specific, for n sufficiently large, probability that this guy belongs to E is greater than half. Okay, so this guy is greater than half. If you make this new denominator smaller, you will only make it larger, therefore you will only reduce things. So, and also this is, if you replace it with something smaller, you will only reduce this probability. Therefore, the right side above can be bounded further as this is, so this guy here is further bounded below by 1 minus 2 probability under this independent IID Gaussians. What is the event that we are looking for? We are just looking for this log. So these are all independent Gaussians. So this also factorizes nicely. So summation t equal to 1 to n log fx tilde t y tilde t, because tildes are odd IID, x t y t by fx tilde t x t fy tilde t y t less than lambda minus log of 2 is log of half is 1, so this is lambda plus 1. Log of half is minus 1, so this is lambda plus 1. Okay. Choosing. So now again, so this is holds for all n sufficiently large. This is for all n large. Okay, so now choosing this lambda, we can choose lambda to be expected value of this guy minus something small. So lambda equals to, let's say we choose it to be we want this to be smaller than some epsilon. So we choose lambda to be the expected value minus something small, let's say. Choose lambda equals to, let's say, n times expected value of this guy. So what's the expected value of this guy? Whatever it is, we'll come back to that. That's just a divergence. Expected value of x tilde t, x tilde t, y tilde t. So they're all IID, so I'll just choose t to be 1. Minus something, whatever we want. Let's say minus something very small, eta. So we choose it to be this. Okay. And maybe even minus 1. So the probability that you are smaller than the expected value, sum of IID is smaller than the expected value for n sufficiently large, is arbitrarily small. For all n sufficiently large, this guy here exceeds, so this probability here is less than epsilon. So this guy here exceeds 1 minus 2 epsilon. Okay. So we have this bound of 1 minus 2 epsilon on this guy. Thus, by the single shot G-utility lemma. So what is that lemma? This is the statement here, which says that if you show this lower bound of lambda greater than 1 minus epsilon, then you have a code of size 1 epsilon to the power lambda with average probability less than 2 epsilon. So now we have shown it. We can find, or there exists, we may not be able to find it algorithmically. So there exists a code of size 2 epsilon 2 to the power lambda with average probability of error less than 2 epsilon. Okay, but epsilon is arbitrary, but what is the rate of this code? So this is the size, and so the rate is roughly just this. So what is this quantity? So it turns out that this quantity is exactly, as you can recognize, is exactly the mutual information, because it's a divergence between joint and independent. So this is the mutual information between x tilde and y tilde. And this again is h of, both of them have densities now. Y tilde 1 is obtained by adding Gaussian noise to a Gaussian x. Remember that x tilde was Gaussian, right? So this x tilde was, the way we generated x tilde, it was the Gaussian with mean 0 and variance p minus eta. And this is the calculation which we had done earlier. So this y becomes a Gaussian with variance with mean 0 and variance p minus eta plus sigma square. And then this guy is just a Gaussian with variance mean 0 and variance 2 pi sigma square. And so the rate that we attain, therefore, so when we take this limit and divide by n and take limit n going to infinity, so half log 2 pi e p minus eta plus sigma square by sigma square minus eta for this part is an epsilon achievable rate or 2 epsilon achievable rate for every eta and epsilon. So we can take limit eta going to 0 and then we can take epsilon going to 0 and you will get that half log, oh sorry, this guy goes away, and then we'll get that half log 1 plus SNR is achievable. So this implies, yeah, this is just the difference of these two things. Implies Cp sigma square exceeds half log, because we can take limit eta going to 0. This is true for every eta greater than 0, therefore also for limit eta going to 0. Note that achievable rates are defined as supremum of achievable rates. The capacity is defined as supremum of achievable rates. So when you take supremum, you can take limit eta going to 0. So you get P plus sigma square by sigma square. Okay, so that's what we wanted to show. So all we did in this proof is use this lemma again. This shows the power of this lemma. Earlier, when we were using this lemma, we generated the code words using IID distributions. But now we want the code words to satisfy certain power constraints. So we still generate some random variables from IID distribution, but then we condition them on this event E, which is the event that code words satisfy power constraints. Okay, and the distribution is chosen carefully so that with large probability the generated code words will satisfy power constraints. So you back off a little bit from this power constraint, and then you get those code words, and then the same single shot lemma can be applied. Okay, of course you can worry about this conditioning, but what we show in this proof is that this conditioning only changes thing by a small number. It just probability of this event comes in, log of probability of this event comes in, and otherwise we still need a lower bound on the log likelihood ratio of the independent distributions. Only the small additional term is there, which we make a constant, and these constants don't matter because lambda grows with n. So when you divide by n, take limit and going to infinity, these constants disappear. Okay, that's the main idea of the proof. Okay, so to conclude, we have shown the converse. Earlier we showed that any code must have the capacity must be at most half log 1 plus SNR, and now we have shown that capacity is at least half log 1 plus SNR, and between these two we have completed the proof of capacity of additive Gaussian noise channel. So yes, this is a very famous formula, this half log 1 plus SNR formula, and now we know the precise context in which this formula holds. It's the capacity of the additive Gaussian noise channel. Okay. See you in the next lecture.